All right, hello. We are going to go through 3.05 right now, just for a nice little video that'll kind of go through the various naming and formula writing rules that we have for our ionic compounds, on top of going through and just doing some of the structures for these ionic compounds when those ions are formed, how those ions are formed, and a little bit of multiple choice action there. So I'll only do a couple from each section, just because you'll use those to work through any of the other ones that aren't listed here. But for the first one, and even before we start, I kind of want to make a couple of just general references, specifically to our periodic table, because I want to make sure that everybody has the ion charge at the top filled out. Remember, group 14, we don't really form ions. They bond a different way, so we're not too worried about those right now. But there are some transition metals that do exist there, that do act a certain way, kind of like tin and lead there. But a lot of our transition metals have their possible charges on the in the element box themselves. So we have all of the metals. Remember that the dividing line on the periodic table is kind of this staircase, this bold staircase where our metalloids are. And we know that to the left of that are all of our metals and stuff. So even though something like lead and tin are not necessarily color-coded as transition metals, they are included in that middle bunch right here. So pretty much everything to the left there. But of course, our group 1 and 2 elements always form the same charges. Hydrogen's not a metal, so don't worry about hydrogen. But our alkali and earth metals form +1, +2 charges respectively. Aluminum is always going to be a +3 charge. And then once we get to the right side of our periodic table, that right side of that staircase here, we start seeing our nonmetals, which are going to be forming our negative ion charges. Going to the back of the periodic table, you have all of the common charges for a bunch of our common transition metals that we'll use. We, of course, focus on the name and the Roman numeral. Don't worry about the Latin names there. And then, of course, we have our only positive polyatomic ion, which is ammonium there, that we'll be using. And then all of the anions, all of the negatively charged polyatomics are listed over here. So again, how do I know when I use these as opposed to something on the front of the periodic table? It's usually based on the number of elements that are in our compound. So just a nice little review there. So hopping back over here, simple binary compounds are just the compounds that have only two elements there. That's where the term binary comes from. And then simple is that all of these metals are going to have a set designated charge that we know. They aren't transition metals. So we know something like calcium has a +2, chlorine has a -1, so on and so forth. But when I name these, all I have to do is name the metal as is. It is not a transition metal, so we do not need any Roman numerals to designate the charge. And then, of course, because chlorine is the nonmetal here, and it is by itself, it's not a part of a polyatomic group, then we take chlorine's name and we just change the ending to "ine." So it's any time you have our nonmetals by themselves, like chlorine or oxygen, nitrogen, fluorine, phosphorus, sulfur, right? So on and so forth. So doing a couple more here. K is potassium, and fluorine by itself has to change its ending to fluoride. And I know some of you asked in class, why do they do that? And it's to note that these are now two things that are bonded together, as opposed to saying potassium fluorine, where now we don't know whether or not they have bonded or if we are talking about them separately. We'll do another one. Let's do this one right here. We'll do the metal name is strontium, and the nonmetal is phosphorus. We change its ending to phosphide. And some of you in class are like, well, what about these subscripts? Well, they're used just so that we can balance out the overall net charge to make it 0, right? We have to have the same positive total as negative total. So in order to do that, we need 3 strontium ions and 2 phosphide ions are going to be created because of that. So the formula writing itself doesn't really impact the name until we get into those transition metals a little below. But now if I give you the formulas, you can go to the name. We should be able to do the opposite as well. So for something like this, sodium nitride, sodium is a Na plus 1. Nitride is nitrogen, and that is a -3. And then our couple of different ways we can do this, whichever way you want works for you best. That's the one that you should focus on. But we are just more often than not crisscrossing those charges values, right? Not necessarily including the negatives or the positives in there, but just showing an easy way to balance out that charge to get the net to be overall 0. So that tells me that I need 3 sodium for every 1 nitrogen, right? And we can do the paper trick, the notebook paper. We can do it mathematically in your head. You know, as you start to get more comfortable with these, makes it a little bit easier. But for something like barium phosphide, we have a +2 charge. We have phosphorus, which is a -3. And again, doing our crisscross method, you say that we need 3 barium ions in order to balance out the negative charge of the phosphorus ions there. Let's go on to transition metals. Now, the difference between the transition metals and the simple or the metals that are like alkali metals, alkaline earth metals, so on and so forth, those are metals up here that have a designated charge that never can change their charge, and they always form the same ion charge. So we don't have to worry about certain metals taking different charges, but we know that with transition metals in the middle area of our periodic table, they don't form ions exactly the same way as our other metals do. And because of that, we need to designate in the name the Roman numerals for what charge they chose, right? And so as we go through, you're like, okay, well, iron is something that can exist as a +1, a +2 or a +3, right? And so we need to figure out which one it chose in order to be able to accurately name it. So we name everything else very similar. And you see, these are still binary, so we're still talking about nonmetals by themselves, which means that we'll have to change their endings to "ide." But because there are transition metals here, we also need to make sure that we designate what the charge is that they take. And so I go through and I see that this is iron something chloride, right? It's either going to be iron 2 or iron 3. And you will always know the anion's charge, right? The negative ion's charge. So a couple of things that we can do here is to work backwards from that negative charge. And we say, okay, well, I know that each chlorine has a -1 charge. Well, I have 2 of those here. So that means that the total negative side of this compound feels like it's a -2 charge, right? Which means that the total positive charge has to be +2 to cancel that out. Well, since there's only 1 iron here, right? Since there's no subscript written, it's an understood 1. We see that 1 iron alone has the ability to balance out the negative charge of those 2 chlorine. So that tells us that this iron has to have a +2 charge, all right, a +2 ion charge, which would then allow us to put the Roman numeral 2 there to finish off our name. All right. Sometimes you could do kind of like a reverse crisscross method as well to do this. I personally don't necessarily find that to be the best way to do this, because sometimes you'll get into something like copper and sulfur here, where you have copper and then you have a Roman numeral for the charge that copper takes with sulfur, which changes its name to sulfide. But if you did like a reverse crisscross, you would see that, oh, there's only 1 of each, so, it must be copper 1. And that's not necessarily true, because you have to identify what the charge is of that negative anion. So again, working backwards, we see that sulfur is a -2 charge per our periodic table, per the 6 valence electrons that it has as an atom. And then you have to make sure that you balance this out. Well, because we have 1 of each, this one's nice and says, well, if I have a -2 side of my compound, then I need a +2, and that means that the copper must have taken the +2 ion charge here, based on that chemical formula that we were given. We'll go on to this one too, do this one. Similar thing over here. Each phosphorus is a -3 charge. Well, I have 4 of them, which means that I have 4 -3 ions, which overall have a -12 charge on the negative end, which means that we have to have a total positive charge of +12, right, to balance that out. And we got to figure out, well, how are we going to get there? Well, each manganese ion needs to be the same charge. They can't have different charge values. So let's figure out what charge it chooses by taking our total that we need and dividing it by how many we have. And we see that 12 divided by 3 gives us 4. So that tells us that each of these manganese ions must have the +4 charge. And so because of that, now we know what Roman numeral we should use in our name. Here is manganese, right? We name it as is. We need a Roman numeral because it is a transition metal, and it is IV for 4 because the charge was 4. And then, of course, phosphorus by itself is phosphide. I personally think that the name to formulas for these are much easier because it tells you right here. We don't even have to look at our periodic table groups. We could just see what the charge is that these things chose based on what the Roman numerals that were provided are. So we have chromium 3. It tells me that I have a chromium with a +3 charge, and then phosphide is phosphorus with a -3. Those balance each other out. Now, if you really wanted to, you could still crisscross, and you would end up with something like this, right? We would need 3 phosphides, 3 chromium ions. But remember, we want to make sure that our formulas are always in the simplest ratio. So because of that, we are able to actually simplify that to then be just CRP, right? One of each. So you can do the crisscross method, but I personally like to kind of just look and see, well, if I have the same ion charge, positive and negative, well, then they're just going to balance each other out. Then I just need one of each of them. So my formula should be CRP. That's similar here in this case with tin being a +4 per its Roman numeral and sulfur having a -2 charge. You crisscross, you could end up with something like this. However, we need to simplify that, so our actual formula is going to be SnS2. All right, so that's going through adding the transition metals there, and then we're going to kind of put everything all together here with the polyatomics, and we're going to say that when we have polyatomics, those are represented on the back of the periodic table, and for the most part, they are going to be anions. They're going to take the place of the negative nonmetals, but there are some instances which you'll see where we use our positive polyatomic, which is ammonium. But going through this, let's do a couple of these. How do I know when there's going to be a polyatomic? Well, up here, we were talking about strictly binary ionic compounds, and that's when we're just taking 2 elements and putting them together, right? 1, 2. All right. Again, you can think easier. Each capital letter in a formula represents 1 element. And now when we get to the polyatomics, we end up seeing that we have 1, 2, 3, right? Anytime we have 3 or more elements in our compound, we know that we'll have one of those polyatomic ions somewhere in there. And in this case, it happens to be the NO3 group right here. So as we're naming this, again, I have to identify, so again, putting it all together, I have to identify that iron is a transition metal. Now, because of that, my transition metal rules apply when naming. Iron must have a Roman numeral associated with it to designate its ion charge. And then the beauty of the polyatomics is that these groups, they have their own particular name. So this group is called nitrate when I have one nitrogen attached to three oxygens. So we don't have to do any like name changing there. It already has a changed name. But we can figure out the charge of the iron so that we can get the Roman numeral correct by working backwards, just like we did above, right? And we can say that each nitrate ion, if I have three of them, gives me an overall negative charge of -3. And because there's only one iron, it must be able to balance that out, so it shows the +3 ion charge there. Something like right below it, calcium and carbonate. I know that that's one of my polyatomics because there are 3 elements in the formula name, or the formula for calcium and carbonate when they join. So I take my name of my metal, and I take the name of the polyatomic ion that is associated with it in that formula. The reason I did not need to put any Roman numeral there is because calcium is not a transition metal, therefore it does not need to show what charge it takes. It always takes a +2 charge. All right, so again, only using Roman numerals when you have the transition metals present. All right, something like over here, NH4, right? NH4, I know that there's a polyatomic here, but you see that our group is actually in the front this time, and that's because in ionic compounds, you always have the positive ion, then the negative ion, right? In that order. And usually they're metals with nonmetals, but in this case, ammonium actually acts like a metal because it's a positive ion. So we use ammonium as the group here, and oxygen is by itself, so we take and we change the ending to oxide. All right, let's do one more. Why not? Well, let's do this one. So here I have 3 elements. I know that I'll have a polyatomic in here somewhere, right? 3 or more elements mean that I'll have something that's on the back of the periodic table there. Sn is tin. Tin is a transition metal, so this one will need a Roman numeral. I know that OH is a -1 charge. It is a hydroxide group, right? And we can just kind of search for this. And we know that even though hydroxide doesn't end with ate or ite, it is still a polyatomic. And so we have 4 of these -1 ions based on how many are in the formula, balance that out. Therefore, that's a total negative charge of -4, which means the total positive charge has to be +4. Since there's only one tin, this one tin must have a +4 charge to be able to balance out the -4 OHs by themselves. All right, now let's go to the bottom part here. I'll just do them all here. For mercury, mercury 1, again, tells me there's a +1 charge. Sulfate, -2 ion charge. You can do the crisscross method, notebook paper method, mathematical method, does not matter to me. Whichever one you prefer, please use. Mercury's mercury, Hg. I need 2 of those to balance out one sulfate group. Now, you'll note that sometimes our groups needed to have parentheses around them, and sometimes they did not, and that's based on if we need multiple polyatomics in a chemical formula or not. In this case, SO4 has a -2 charge that doesn't necessarily mean that it needs parentheses around it when you see that you only need one of them. And that's why I will usually not incorporate parentheses around that polyatomic if I only need one of the group. But you can also see that even though I only need one group for sulfate, I still keep this 4 there, all right? I don't just get rid of it because that 4 is part of the identity of the sulfate ion itself. So I can't change that. So that's why putting parentheses around those polyatomics does lend itself to remind you that whatever numbers are associated with those are always going to be there. They cannot change. And if I need to change the amounts of something, then I have to do it outside of those parentheses. Iron 2 thiocyanate. That 2, again, tells me iron's a +2 charge. Thiocyanate is a -1 ion charge. Again, that's on the back of the periodic table. You end up with iron here. And now, because of and you can do the crisscross method if you want, we will need 1 iron, and we will need 2 thiocyanate groups. And because we need more than 1, we have to put it in parentheses. All right, so now let's go on to this next one. Rubidium, that does not have Roman numerals here because rubidium will always have a +1 charge. Nitrite, right? Different than nitrate, different than nitride as well. And the next one we'll do. Nitrite has a -1 ion charge. And so these go together really well. They could just balance each other out, one of each. And the nitrite group is NO2. All right, if you wanted to put them in parentheses, you could, but you have to make sure that you keep that 2 there because it is a part of the group. And then ammonium, you get used to identifying that as our only positive polyatomic. That's a +1 charge. And nitride, so you end up noticing that there's nitride. There can be a nitrate. And there can be a nitrite. And so these ions are all different. Nitride is nitrogen itself that has a -3 ion charge. Nitrate, NO3 with a -1. Nitrite, NO2 with a -1 ion charge. So please pay attention to the suffix so that you know which one you are working with. So our ammonium is bonding with the nitrogen ion here. Ammonium is an NH4 group. I do my crisscross method. And I notice that I need 3 of those ammonium groups, and I only need 1 nitrogen. All right, so again, making sure that you're paying attention to those suffixes are going to help you identify the appropriate ion that you are using here. All right. Down here, we have just I'll do maybe one of these because it's very similar gist over how these ions form. So let's do something like aluminum and oxygen. Aluminum, I want to show the electron transfer. Now, aluminum has 3 valence electrons, and it's trying to bond with oxygen that has 6. All right, not good practice there. I was doubling them up before, but you should have 1 on each side before you double them up. But what happens in these ionic bonds and why all of these ions form, right, when they come together is because the metals want to lose their electrons in their valence shell to feel like they have a full octet on the inside, and then nonmetals want to gain, right? And so they work well together. But to show this, we have a transfer of electrons from metal to nonmetal. Right? But now what we notice is that sometimes my metal will have too many electrons and I'll need to start adding more nonmetals, or vice versa. So all these images are showing us is how to draw this electron transfer so that we can visualize why these ions are forming. And then, of course, how many of these ions need to form so that everything feels full and nothing is kind of left out. So we notice that the 2 electrons that oxygen wanted, it gets from the aluminum, but I'm going to need another oxygen in order to accept this electron from aluminum. Well, now the aluminum's good, and now the oxygen's not, so now I need to add another aluminum. That's going to bring another 3 valence electrons with it, right? Now that oxygen's good, so on and so forth. So just making sure that everything has what it needs. Everything is gaining, losing what it needs. And then, of course, we have what we are calling a Lewis structure, but it's really just all of the ions formed based on the transfer of electrons that goes there. So both of these aluminum lost 3 electrons to form their +3 ion charge, and then all 3 of these oxygen gained 2 electrons to form a -2 ion charge. Let's see. Work smarter, not harder. All right, but then we show that once that transfer occurs of electrons, no longer do we have electrons in the outer shell for aluminum. And then, of course, we have a full octet for each of those anions that formed for the oxygen. Using this drawing, right, we have, and you'll see sometimes also that, you could bracket these in, and it makes it look a little cleaner. You don't necessarily have to do that, as long as you kind of identify that those are the ions that form. I'm cool with that. But when we have 2 aluminum for every 3 oxygen ions, that balances out very nicely. And then, of course, naming this aluminum is not a transition metal, so we do not have to worry about Roman numerals. And oxygen is going to change its ending to oxide. All right. Last but not least, a couple of multiple choice questions. If an atom X has 3 electrons in its outermost shell, which ion will be formed? So, something that has 3 valence electrons. You think which is easier for it to do to form its, or to fill its octet? Do you lose those 3 or do you gain 5 more? You have to lose those 3. Once those 3 end up going somewhere else, we are now becoming more positive by 3. So remember, it's a little counterintuitive with electrons, but that is going to give us the ion charge of a positive 3. Nonmetals are on the right side of the periodic table. They always prefer to gain electrons, so you can eliminate C and D. And of course, metals are on the left side. They prefer to lose electrons. So we have B there. Cations. Cats have paws. Let's draw a picture of a cat. Paws. They are positive. I'm positive. All right. So that you will always remember. So cations have a positive charge. We know that's not B or D because electrons are what? Well, in order to form a positive charge, electrons have to be lost in order to have more protons than electrons within the ion itself. Therefore, A helps us fill that in. Anions are negative, of course, because electrons are gained. Atoms bond, even number of electrons. Nope. Sometimes we don't need an even number of electrons. An outermost energy level that is full. Absolutely. That's why things bond. They want to work together to figure out how to fulfill their octets. An equal number of protons, no. And then, of course, more electrons than either protons or neutrons, no, not necessarily. So that one, again, making sure you note outermost energy level full of electrons. And last but not least, which of the following statements about ionic compounds is true? Select all that apply. Ionic compounds are very strong due to electrostatic forces of attraction, right? The positive and the negative really like to be held together, so they have a strong force there, so that's true. They're formed due to a transfer of electrons, right? And we showed that up here, all right? Transferring electrons from metal to nonmetal, so that is true. Metal ion always comes first in the names and the formulas of ionic compounds. That is true. Transition metals need Roman numerals when naming to show their ion charge. True. And polyatomics must be placed in parentheses if multiple are needed. Okay, so everything is true there. Those are kind of some of our naming and formula writing rules as well. So hopefully this helps. If you need me to go through any others, then please let me know, and I will. One thing that I do want to make sure that I mention is the idea of these transition metals having these Roman numerals. The misconception could be that those Roman numerals are how many of those ions that we need. So a very common mistake would be seeing this 2 here and then immediately saying that there are 2 copper. That is not necessarily true. It's going to be based off of what that ion charge is. So that tells us that copper has taken a positive 2 ion charge. It's not telling me that there are 2 copper here, right? That is not what that is. So we just go through, crisscross those charges. We end up seeing it's quite the opposite. We actually need 2 bromine for every 1 copper ion. So just be careful for that. But that's it. Let me know if you have any questions.